Another example of the series that we will see is called telescoping series. You will see why. So the problem normally is asking us to find the sum of the series if the sum exists. So the series given here, 1 divided by k factor of k plus 1. K goes from 1 to infinity. So this series is called telescoping. You will see very soon why. The general term is obviously 1 over k factor of k plus 1. As is, it's a little bit complicated to see what's happening. So this is reminding us of partial fractions. So we will use partial fractions to split this ratio here into two pieces, and we will need to find the corresponding values of the constants. So 1 over x factor of x plus 1 by partial fractions, we know that we have two linear terms. We have a over x plus b over x plus 1. So now we need to find a and b. So we cross multiply by x factor of x plus 1. So we get 1 equal a x plus 1 plus bx. As usual, by partial fractions, we will choose wisely the values of x at which to evaluate this expression. So first choice is x equals 0, because this will remove the b from the equation. So we have 1 equal a, 0 plus 1 plus b times 0. So this is a, so this means that a is equal to 1. Again, we use our equation, and now we choose another value of x wisely, x minus 1, and then this will help us find the value for b. So we have here minus 1 plus 1, 0, so this part here goes. We have minus b, so 1 equal minus b, it means that b is negative 1. So we have both coefficients for our partial fraction. Obviously, for x's going from 1, 2, 3, 4, 5, 6, this partial fraction is exactly the same as our general term. I know here we are using x's 0 and negative 1, even though here k is from 1 to infinity. This is discrete. This is like a function of x. And for each value k equal 1, 2, 3, 4, 5, we actually reproduce our terms in the general term. So that there's nothing problematic here. We can just go to the partial fractions, find the values of the coefficients, and then rewrite the partial fraction in two pieces. So our general term now is split in these two pieces. That means that our telescoping series, so the general term is written this way. So now you will see why it's called telescoping. It's compressing a little bit. There's a lot of cancelling. So here for k equal 1, we have 1 over 1 minus 1 over 2, right? For k equal 2, we'll have 1 over 2 minus 1 over 3, etc. So now we will see the use of partial sums. We already said that the sum of the series is equal to the limit of partial sums if the limit exists. If the limit exists, we get a fixed number, so that's the sum of the series. If the limit of partial sums does not exist, then the series is divergent. So let's see what's happening here. So I have my partial sum n, and you see I'm going from 1 to n. The series itself goes to infinity, but my partial sum goes from 1 to n. Okay, so let's see what's happening here. So when k is 1, I have 1 over 1 minus 1 over 2 plus. So this is a sum of first n pieces. So when k is equal to, I have 1 over 2 minus 1 over 3 plus. The next term, when k equal 3, I have 1 over 3 minus 1 over 4 plus. The next piece, number 4, I have 1 over 4 minus 1 over 5 plus 1 over 5 minus 1 over 6 plus, and we keep going. So here I will add. So let's say we are at n minus 1. So I have 1 over n minus 1 minus 1 over n plus, in the last term, n, 1 over n minus 1 over n plus 1. So what we observe here is that some of the terms are repeating but with different signs. So here I have negative 1 over 2 and I have positive 1 over 2. So these two will cancel. Negative 1 over 3, 1 over 3. These two will cancel. Negative 1 over 4, positive 1 over 4. They will cancel. Negative 1 over 5 and positive 1 over 5, they will cancel. So you see, a lot of these terms will cancel. This guy will cancel with people before. And then negative 1 over n cancels with 1 over n. So that's why it's called telescoping, because all these pieces actually disappear. So this is equal to, the survivor here is 1 over 1. Then these two cancel, these two cancel. So everybody is cancelling. This one is also cancelling with the previous guy. Minus 1 over n and 1 over n cancelling. So the survivor here is 1 over n plus 1. So this is my nth term of the partial sum. Now we know that to find the sum of the series is the limit of partial sums if the limit exists. So let's compute limit when n goes to infinity of Sn is limit when n goes to infinity of 1 minus 1 over n plus 1. Obviously this term here goes to 0, so we have 1 minus 0, which is 1. So the telescoping series, now you see why it's called telescoping, because a bunch of terms are just removed. So my telescoping series, 1 over k factor k plus 1, which is equal to this, right? So I will write it, we don't need to, but I will write it once. So this sum is equal to 1. So this series is convergent. How do we know? Well, the series is equal to a number, right? The sum of the series is equal to a number. That way we know that this series is convergent. So again, the expression looks a little bit complicated. Then we realized that actually we could use partial fractions to split it in two pieces, and then we find the coefficient and we replace the general term by the split piece, and then we expand essentially the partial sum Sn. So from 1 to n, we write it out to see who will survive. So in this case, the first guy survived and the last guy. And then we take the limit of partial sums. If the limit exists, in this case it does, it's equal to 1, that limit is actually the sum of the series. So the series here is equal to 1, and it's convergent series. In a case where, for some reason, the limit here would not exist, then we would say the series is divergent. So let's have another example of another telescoping series. This one will be a little bit different. So here we have use of partial fractions to rewrite the general term, and then use that to write the partial sums. So let's say we have something like this. So what happens here? A k is okay. I wrote n, should write k. ln k over k plus 1. So what do we do? Well, we know the rules for log. So those are the properties. So we will use them. So you see, in this situation, we didn't have to use the partial fractions because just by using properties of the log, we were able to rewrite the expression of the general term in a convenient way that will help us cancel things. Okay, so now partial sum Sn. So you see, that's why we use K, because we have Sn, so that way we don't mix these expressions, the coefficients, the indices. So we have this, so I will write it this way also. Obviously we can start with this, it's faster, but I'm just doing it step by step. It is super important to have the brackets correctly written. Fundamental. So now we know that when k is equal 1, we have the first term is ln1 minus ln1 plus 1, closed, plus the next piece when k is equal to is ln2 minus ln2 plus 1, 3, plus k equal 3, ln3 minus ln3 plus 1, 4. Right? Plus ln4 minus ln5. So obviously we see the pattern a little bit. So let me write for n minus 1. So ln n minus 1 minus ln n plus the last piece for the Sn is ln n minus ln n plus 1. Okay, so now we look a little bit what's happening. We have negative ln2, positive ln2, so they cancel. Negative ln3, positive ln3, they cancel. Negative ln4, positive ln4, they cancel. Negative ln5 will cancel with positive ln5. Negative ln n minus 1 will cancel with ln minus 1. So this guy here, negative ln, cancels with this guy here. So essentially, a bunch of these terms disappear. So that's why it's called telescoping. So this means that the survivors are ln1, okay, it's 0, fine. And then the last survivor is ln n plus 1. So ln of 1 is 0, so I have negative ln n plus 1. So this means that the partial sum Sn is actually equal to negative ln n plus 1. Okay, so let's see what happens here. As n goes to infinity, what happens? N plus 1 also goes to infinity, and then ln of n plus 1 also goes to infinity, and then negative ln n plus 1 goes to negative infinity. So that's important to realize. Which means, since negative ln n plus 1 goes to negative infinity, as n goes to infinity, then Sn goes also to negative infinity as n goes to infinity. Okay, I'll write n cubed. What does it mean? The limit of those Sn, what do we say about this limit? If the terms go to minus infinity, then this limit does not exist. We know that the sum is equal to the limit of the partial sums, but this limit does not exist, since the limit of the partial sums does not exist. Then the series, which is a telescoping series, by the way. So, okay, I'll write it. ln k, oops. Minus ln k plus 1. I'll write the telescoping part so it's easy to see. So this series is divergent, or we say this series diverges, whichever one you like. So you see some of these telescoping series converge and others might diverge. So there is no general rule for this. So we need to be careful. In some cases, we will need to use partial fractions. In other cases, like here with the ln, we use properties of ln. Another example of telescoping series. Here again, I just changed a little bit the name of the index, just to vary a little bit. Before it was k, now we put n for fun. We can put I also, any letter actually works. So the expression is already split, so we don't need to do anything. So it's 1 over radical n minus 1 over radical n plus 2. So it's not n plus 1, it's n plus 2. So the general term here is 1 over radical n minus 1 over radical n plus 2. So the partial sum from 1 to n, and you see now I use I as an index because we need to use a different name from n, obviously. So AI, I going from 1 to n, I just copy general term. So in terms of I now, 1 over I minus 1 over I plus 2. This is just to get used to different letters. If you keep k all the time, it's fine. You don't need to vary much because you can use k here all the time and n upstairs, so it will not be a problem. I just wanted to change a little bit for you to get familiar. So now we expand this partial sum of n pieces. So the first piece is when I is equal to 1, so it's 1 over radical 1 minus 1 over radical 1 plus 2, which is radical 3. Here, so there's the first piece. When I is equal to 2, we have 1 over radical 2 minus 1 over radical 2 plus 2, which is 4. Keep it as radical 4 because it will cancel eventually, so you don't need to write 2 here for nothing, just keep it as is, keep the same format. The third piece is 1 over radical 3 minus 1 over 3 plus 2, 5. So you see the index here, and here is plus 2. So 3, 5. The next one is 4, 6, then 5, 7, 6, 8, etc. So essentially we see that the next one is plus 2 from the previous. So at some point, because n, we don't know how big it is, we will have 1 over radical n minus 2. So the next guy is plus 2, so it's n. Then n minus 1 plus 2, n plus 1, and 1 over n, and 1 over n plus 2 in radical. So you see our term here, we stop at n, we will have n plus 2 at the end. So that's fine. Now we observe that there are some cancellations. So what do we see? 1 over radical 1, we don't see it anywhere. Negative 1 over radical 3, or we have positive 1 over radical 3. So these two will cancel. 1 over radical 2, we don't see it anywhere. So this guy will probably survive. Then we have negative 1 over radical 4, positive 1 over radical 4. So these two will cancel. Negative 1 over radical 5, and then here we have positive 1 over radical 5. They will cancel. Negative 1 over radical 6, positive 1 over radical 6. So you see we are actually jumping one term. So this guy will be cancelled by something here. Okay? That way we see that what's happening is this negative is cancelled not here, but on the second bracket. See, plus 2, that tells us last time when we had plus 1, it was cancelled immediately. Now we jump, so 1, 2. So this gives us a hint. Obviously, if we had something with plus 3, it would be the third. Every third would cancel something. So it would be just a little bit more annoying to write the last part. But as you see, these last parts have n downstairs and we take the limit, so all of this will be 0 anyways. So it doesn't really matter if we don't write so many pieces. So this guy will be cancelled by something before. Now we see 1 over n with the negative sign, and we see here 1 over n with the positive sign. This guy is cancelled somewhere here, right here somewhere. Okay, so essentially this is what we have. So our sum now, partial sum Sn, who is surviving? 1 over radical 1. Then this guy is going with this, disappearing. The other survivor is so plus 1 over radical 2. And then all of these guys are cancelling, cancelling, cancelling. And the survivors here will be minus 1 over radical n plus 1 here, and then negative 1 over radical n plus 2. As we said, these people with n downstairs, when we take the limit, they will go anyways. So the limit of Sn, so the partial sum, when n goes to infinity, is equal to the limit of this expression. So I'll just copy everything. So 1 plus 1 over radical 2 minus this term and this term. So now obviously we take the limit, and the limit is, so this goes to 0, goes to 0, so we have 1 plus 1 over radical 2. We can put it as one fraction, or not, doesn't matter. So this is a fixed number, a real number. So the limit of partial sums is equal to a real number, a fixed number. So that means that our series is convergent. So since the limit of the partial sums is a fixed number, then the telescoping series so I'll copy the series. That series is convergent and is equal to the same value. So convergent series so you see some of the telescoping series are convergent and others are not. So we just need to work our way through, and we use the definition of the sum of the series, which is a limit of partial sums. So we need to write the partial sums, we write them out, and we see which parts are cancelling and which parts are surviving. And you see the surviving parts, those are the one that will give us the limit. So in this case, it's a real number, so limit exists. In previous case, the partial sum was going to minus infinity, so the limit didn't exist. So in this case, series is convergent because the limit is a fixed number, and in previous case, the series was divergent.